Hello. This time I was introduced with this question. Under what conditions does a square real matrix A have complex eigenvalues? So in this context, real means with real entries. Well, for that I want to motivate some ideas in terms of prior knowledge that we have available about these problems. And we will say something along these lines. Recall that eigenvalues are exactly the roots of the characteristic polynomial of A. To put it in other words, this is lambda is an eigenvalue of A if and only if, when you evaluate the polynomial at lambda, that results in 0, where P of t is nothing else but the characteristic polynomial of A. So A minus ti, right, for some symbol t. Now, under this consideration, we know also that the fundamental theorem of algebra states the following. Indicates that every polynomial, non-constant, polynomial uh, with complex coefficients has a complex root. Well, among the complex coefficients, we also have the real coefficients. So we would say something along these lines. A polynomial with real coefficients, of course non-constant, has a complex root well whenever it doesn't have real roots. And for that, I'll provide an example. I'm going to take this polynomial t squared plus t plus 1. Well, this one has no real roots. And how do we know that? Why? Why is this the case? Well, look, it's discriminant. So the one that we find inside the square root sign of the quadratic formula is the following. 1 squared, the linear coefficient, minus 4 times the quadratic coefficient times the constant is equal to negative 3, which is less than 0. So the discriminant is negative, meaning that it has no real roots. So now, really, one of the questions that we would like to answer is, well, can we construct a matrix such that it has t squared plus t plus 1 as its, well, characteristic polynomial. right? That way we will provide at least an example of a matrix with real entries that has no real eigenvalues, but it does possess complex eigenvalues. So how can we proceed? Well, it's through the following observation. If we examine the polynomial that we have here, it's a polynomial of degree 2. So that means that it could come only from the characteristic polynomial of a 2 by 2 matrix. So and we may say, well, but what will be the conditions? Well, there's the thing. If we provide the characteristic polynomial of a 2 by 2 matrix, the quadratic term has a coefficient of 1. So this one is already taken care of. The only place that we have to make some decisions is how do we control the coefficient that goes along the linear part and along the constant part. So for that, let's try to see if we can answer a general question. So what about a polynomial of the form t squared plus a t plus b for a and b real numbers? If we can answer this in general, then we would be able to answer this in the particular case that we are concentrating on. Well, but then look, this case is not so difficult. If I use the following matrix, 0, 1, negative b, negative a, well, then I examine its characteristic polynomial, meaning the determinant of minus t, 1, negative b, negative a minus t. Well, this results in negative t times negative a minus t minus negative b times 1, which is nothing else but t squared plus at plus b. So in this case, it's quite easy. We see that the matrix 0, 1, negative 1, negative 1 has t squared plus t plus 1 as characteristic polynomial. Moreover, this matrix has no real eigenvalues, but it has two complex eigenvalues. And where do they come from? Well, they come as a solution in the complex setting of of the roots of this polynomial. In other words, those have the following form. Which may be written as negative 1/2 plus the square root of 3 over 2i, but also negative 1/2 minus square root of 3 over 2i. And well, with this we finish. I hope that you enjoy it. Let me know if you would like to explore this in the general case. Just leave your comments below or provide a request. Okay? Take care. See you around.